So the next signal conditioning method is filtering, but I'm not going to go through these three most common types of filters. I am going to go straight to the low pass filter. Okay, so a low pass filter is allowing low frequency signals to pass and block high frequency signals. Okay, so this is the construction of your low pass. Your resistor is here and your capacitor is here, and the reactance is equivalent to 1 over 2 pi fc. So if your frequency is low, you will have a high value of reactance, right? You are dividing with a low value of frequency, so because of that, this will look like an open circuit. So you can see here, right? And when it is at high frequency, it will be a short circuit, so you will have a zero output. When you have low frequency, you have an open circuit, you will have an output voltage. So that's how it works. Okay, now you need to take note that the cutoff frequency for a low pass filter is the frequency at which the output of the voltage is 70.7% of the input voltage. Okay, that's where the cutoff values is being measured. So if you look at this next slide, at minus 3 dB, that's where your output is 70.7%, and that's your cutoff frequency. That's why they call it FC. So 1 over 2 pi RC is your cutoff frequency. The R is the value of the resistor and C is the value of the capacitor. Next is the high pass. So this time your capacitor is here instead of your resistor, and your resistor are now measured at the output. So if you look at the formula for XC, alright, so this time for high pass, it will allow high frequency signals to pass while blocking the signal that is low. Okay, so if high frequency, it means that you will have a low value of XC, right? Small value of XC. So when it is at high frequency, you will have a low value of reactance that it will be similar to a short circuit, and you will get a value of the output voltage. But this is when it is low. So you can see here, at DC or low frequency, you will have open circuit. So your V out will be 0 because you are measuring across a resistor. So same thing, the value of the cutoff frequency is when the output of the voltage equivalent to 70.7%. Okay, it will go upward until it reaches this point. See, if you look back at the low pass, it will allow low frequency, but then once it reaches this point, the 70.7%, it will block. So this is the cutoff frequency for low pass. So it's going downward for this case, and the high pass is upward. Okay, in addition to high pass and low pass, you can also allow frequencies from certain range to pass, right? So in this case, this is known as band pass filter. So by connecting or cascading together a single high pass filter connected with a low pass filter, we can produce another type of passive RC filter that allows a selected range or band of frequencies. Okay, so this is known as the band pass filter. You need to connect the high pass and the low pass together in series. So this is the high pass, and this red box is your low pass. Okay, so of course the band pass have two cutoff frequency. So the first one is 1 over 2 pi R1C1, and then you have another one, 1 over 2 pi R2C2. So let's look at the next slide. So in this case, remember that the high pass is upward, right? So that's why you have the high pass first. Okay, so it allows the first frequency, which is the high pass frequency. That's the first one, and then allows to pass and then connect with the low pass. So low pass is downward, right? So the downward part is your second FC. So band pass have FL and FH, the low frequency and the high frequency band pass. So the high frequency is given by the low pass filter, and the low frequency part is given by the high pass filter. Okay, so take note on that. It's very simple. The low cutoff frequency is given by the high pass filter. The high cutoff frequency of your band pass filter is given by the low pass filter, right? So that's how you can remember. Okay, so let's look at this example. So this question said that a second order band pass filter is to be constructed using RC components that will allow a range of frequency to pass above 1 kHz and below 30 kHz. So this is the FL and this is the FH. So this is very easy actually. C1 and R1 is related to the high pass filter. R2 and C2 is a low pass filter. So I hope you can try and solve this example, okay? So if you have band pass, surely you will have band stop. You are going to block a band of frequency. So this time, you still combine low and high pass filter, but you are going to combine it in parallel. So you can see here the band pass just now is connected in series, right? But for the band stop, it will be in a parallel type configuration as shown here. Okay, so for band stop, it has the low frequency and the high frequency, and most importantly, the cut-off frequency, at which the cut-off frequency can be calculated using the formula FL multiplied with FH and square root. And that's how you can get the cut-off frequency for the band stop filter. So low pass will provide the cut-off frequency, which is the low part, okay, and the high frequency will be provided by your high pass filter. So this time it will follow the notation. FL will look at the low pass filter and the FH will look at the high pass filter. Okay, just now I have shown you a number of circuits using passive components, which is the resistor, inductor and capacitor. However, filters can also be constructed using active filters, where you combine R, L and C together with an active component such as op-amp. So you can see here, so this is the low pass filter stage. So initially, without the active component, this will be the output voltage and it will be lower, right? It will be less. So because of that, you need to amplify it. So that's why you include this non-inverting configuration. You include this op-amp in order to increase the gain of your filtered output voltage. So the gain for non-inverting is 1 plus R2 over R1, the resistor at the feedback path over the resistor here, R1. So that's the non-inverting configuration. So in order to know what is the gain, you just need to find out what is the output voltage, just V out over V in. Okay, so the output voltage at the cut-off frequency will be higher because you are going to multiply with the gain as well. Okay, so let's look at this example. So this is a non-inverting active low-pass filter circuit that has a gain of 10. Okay, which means that the AV is equivalent to 10. Right? And you are already given what is this resistor here, which is your R2. Okay, the feedback resistor. And a high frequency cut-off or corner frequency of 159 Hz. So this is your low pass filter, which means that the cut-off frequency is 159. You want to calculate what is C1. Okay, so this is actually very straightforward, but I'm going to show you how to calculate this. Okay, so let's start with finding C1. So let's use the cut-off frequency given by 1 over 2 pi RC1. So the cut-off frequency given is 159 Hertz. Okay, and the R is 10 kilo ohm. So 10 to the power of 3. So you bring C1 over as the subject, bring down 159, and you will get C1 equivalent to 1 times 10 to the power of minus 7, which is equivalent to 100 nanofarad. So that's how you get the 100 nanofarad. Okay, so next is finding what is the R1. So you're going to use the gain that is given. Alright, so from the gain, 10 equivalent to 1 plus 9 over R1. Okay, because your R2 is 9. Okay, and then you will get 10 minus 1 is 9. So you are left with 9 over R1, and you will get R1 equivalent to 1 kilo ohm. Okay, so like I say, this is very straightforward. So similarly, for high pass filter, you can also amplify the output of a high pass filter using the same configuration, non-inverting. And in this example, again, this is a high pass filter. It stated that it has a pass band gain of 2, which means that the gain AV is 2 and a cut-off frequency of 1 kHz. I will show the solution as well. So in this question, you are asked to find what is the resistor R3 given C1 as 10 nanofarad. So again, we use the cut-off frequency formula. Okay, so you can see here 2 pi RC1, this is R3, and the cut-off frequency is 1 kHz, which is 1000 Hz. Okay, so we bring R3 as the subject, and you have this equation, and finally R3 is equivalent to 15,915 ohm, or it is equivalent to 16 kilo ohm. So again, R1 and R2, the thing is, value of the gain here is 2, right? So if I use the gain equation, 1 plus R2 over R1, and it is equivalent to 2, and 2 minus 1 is equivalent to 1, you will get R1 equivalent to R2. So it means that in order to get a gain of 2, just choose any values and make sure that R1 and R2 is the same value. So that is the conclusion of this design. So what if we have designed the high pass filter as follows, where your resistor here is the same, right, for the gain of 2 just now. So we want to make it a band pass filter this time. So what you need to do is just connect it with a low pass filter. And based on these values, you can get the values of the low and high frequencies. Can you calculate those values? It's very easy because this is the FL and this is the FH. So I think I leave it to you to calculate those frequencies. Okay, so next, as I've mentioned just now, for band stop, you are going to place the low pass and the high pass in parallel, and then you're going to connect it with an active component, which is the op-amp, and these two are connected as summing amplifier here. Okay, so the low pass is connected like this, alright, and then this is the high pass, and then the output is fed to the op-amp, and this output is also fed to the op-amp at the same node, right? So that's why this is the summing amplifier. And then the low cut-off frequency FL is this calculation, 1 over 2 pi, 8 kilo ohm multiplied with 100 nanofarad, you will get 200. And then for the FH is 1 over 2 pi multiplied with 2000 and 100 nanofarad, and you will get 800. And therefore you can calculate what is the cut-off frequency, which is equivalent to 400 Hertz. Okay, if the question asks you to construct a band stop filter configuration using active devices, because this is an open book exam, you can just construct this circuit. However, you have to choose the values of the resistors and capacitors based on the frequencies that I have given to you. So that is the only challenge. Okay, as for the configuration, as for the schematics, it is all on the slides. I hope that you will not face any problems in terms of the calculation. So that's the end of the signal conditioning for filtering. Thank you. Assalamualaikum.